is that. So that's not a complete yet. That's been using 36 things
Okay, we didn't actually finish everything like at the end, so we still have one question left behind. Actually, let's see if I can go. What is that? So we were talking about the problem that like if you have many matches like here, and you're trying to warp this object here into another scene. So then like first we get these feature points and we know how to get the matches. And we basically the matches, of course, like we get the feature we get the key points, we get the descriptor, we can map the features using maybe just a dot product or something, find the correlation. But as we mentioned, if you remember, like to avoid some wrong matches, we can compare the best match with the second best match. If it's about certain threshold, we consider it a good match. But still, like we will, like here, you will occasionally get some really bad matches, right? Like this one match here. So if you just get all these matches and try to solve the set of linear equation, if you remember last time, basically to solve the homography parameters, we won't be very stable, and sometimes we'll get something totally off. For example, if we include some of this solution like this. So the standard way to avoid this, to tackle this, is to basically like we'll just if you remember, for example, if we are matching a homography, we don't need all these points here, right? Of course, we can use more than enough, but in general, we don't need all these points. So, for example, for homography, we just need 5 points, something like. So then we can take 5 points and randomly take 5 points. Then like we will have a model, right? And then we will see like whether this model is good or bad, like according to the rest of the matches there. And this idea is known as the RANSAC. So basically, I can just arbitrarily pick 5 or 6 matches here, then I'll form a model, right? After I form a model, then I can use the rest of the matches and verify whether my model is correct or not. Does it make sense?
What did you say the method was called? RANSAC?
Yeah, something like, let's see if I have the name here. Oh, okay. No, I don't have this. RANSAC. Yeah. Why is okay here? This actually stands for random sample consensus, something like. Yeah. So this is just a simple illustration, right? So let's say here, like I have all these matches here, and if I just try to form a translation, so I just need 1 pawn to match. So let's say I take this pawn and build. I just need one match to build a model. So I take this, build a match, and then and for this model, like this blue one, if I verify for the rest, this blue one, it just give me code saying it's a correct model, and this red one saying it's incorrect. Then if I take another one, let's say I take this one as try to build a model, this time like all of them like saying that it's incorrect. So then I can say the first one is a good model, the second one is not a good model. So it's a very simple idea. So I just repeat it many times, right? So every time I just keep the best model. So only when I have a better model that give me, when I validate that like I have more matches, that consensus is not a verb. With the model, then I will just keep that better model now. So that's basically the idea, very simple. So then I guess the only question left is like, in general, how many samples do I need? Samples here, I mean like each time I will grab a number of matches, I would consider as one sample to build a model, and how many repeated kind of sampling I need to do in general to up to, let's say, if I want to have my model to have 99% of accuracy. So we can estimate that if we have a general idea, let's say, how many of my matches are basically inlier in the sense, say, for example, this one here, if I go back to here, how many of them are inlier if you just have a quick scan of these matches here? Here.
How many what?
Inliers. So you just think of the statistic, like when sometimes we say inliers and outliers. Outliers are actually the bad one. Yeah. That's the not the. Or like I should say, like how many of them are the good matches here?
5.
Yeah, 5. These 5 are the good one. I think like I have this. Like okay, I have the color here somewhere. Like this yellow and blue are the good one, and then the rest 2 are the poor one. So if I consider how the percentage or like the ratio of inliers is about, here is like 5/7. So if I can estimate this number, let's say I know this number kind of roughly, say I have the fraction of inliers W, and then let's say N is the number of points to build a model each time. So for example, like okay, this you can ignore this 2 for lines. This is think of like if I'm doing translation, I need 1 match, or like if I need to form a homography, I need 5 matches, something like. So N will be 5 in that case, and K will be the number of samples. Is how many times I'm going to repeat this process. Then just think of the probability like carefully. So if the number of fraction is like W inliers, so for a single sample that is correct, that I need all of them to be correct, right? So that I will need W to the power N, and then like then therefore like the probability the model is fail will be okay. Well, I skip. It doesn't matter. So probability that I do K repeated models and all of them fail will be 1/Wn to the power K, right? Is that right? Yeah, 1/Wn will be the probability of failure. Probability of failure for one model. Right? So all of them fail will be like 1/Wn to the K if I do this repeat K times. Does it make sense? So then I just need to choose K large enough, right? As long as K is large enough, then it will work. So generally, we are like, why this slide is not the slides I'm supposed to have? But anyway, I didn't save it. I don't know. So so I can basically for example, if I want this to be like let me just pull out even though I don't like this pen here. So if I want to have my model to be 99% accuracy, then I should just have like 1, that's why I don't like this. 1 minus this way, 1 minus Wn to the K to be larger than 0.99, something like that, right? So then it would be good. So I have no control of W unless you have a good descriptors and so on. I have no control with the N, but I have a control with the K, right? So if I have this value that I want to be 0.99, I just need to pick a K that give me larger than 0.99, something like that. So this is a table, actually, or like, you don't need a table, you go back to it, but this can be verify your idea. So let's say if for example, if my features are quite accurate, let's say it's 10%, only 10% of them are incorrect, so number of fraction of outliers is only 10%, or like W is like 0.9. Then if my model size, let's say if I'm doing like a homography, then my model size can be just 5, then I just need to repeat this 6 times, let's say. But if my W is pretty bad, let's say if my W half of the times are incorrect, then I need to repeat this like 100 something times, so that like about like 150 times, so that like my model, I can ensure my model is like 99% accurate. So that's about it. So it's pretty simple actually. In general, it's not that bad. Like you see, like you need to repeat it many times, but this computation is pretty quick, because if you remember, like we match the model, it just pull out some points there, and we have a very small kind of linear set of equations. So you just do a kind of like if you remember, a pseudo-inverse matrix multiplied by a vector, and that pseudo-inverse matrix is only 3 by 3. It's super quick. So it's like we're talking about like order of like tens of milliseconds or like less than that. So therefore, like you repeat 100 times, it's not that bad really. So that's it. Actually, that's what we have. The last thing we talked about last time. Let's look at some. Let me give you some demo here. So I'm thinking whether I can capture you guys or not while putting you guys on YouTube. Supposedly, I need to get permission from you guys. So I'm very careful that I didn't make any. So, but let me. I guess it would be better if I move to somewhere. Do I have already some? Let's see. No, maybe I shut down all the. Just take a photo first. Find something to take. I need something that is relatively stable. So maybe, okay, maybe I'm not sure the Windows will work. Let me try that. Windows. I think it's pictures, webcam. So, let's see, let me find, where's my, I think, is that shift? Maybe not. For this, well, maybe this one. So, okay, this is just a simple example. Okay, I may put up another homework, trying to combine these things together with descriptor and maybe form a stitch the image. So let's see. Okay, I haven't. Okay, this is camera 1, right? Okay, I need to shut down my here. So this is just a simple example. As you can see, like you should get pretty familiar with this now. So I just create some descriptor here and change to like kind of grayscale image, and then I detect the descriptor and show that. And let's see. So this is the one with the descriptor here. So just create some kind of descriptor. So there's a number of them that you can. This one I'm using surf, right? No. This one I use this called brisk. But yeah, I can use surf as well. So let's see. The other one, I think I'm trying to do some match. So this time I use surf. And I use surf because I find that there's a command for me to match descriptor. And let's see. Oh, okay. I have the old one is my bottle. Let me try to create. Let's see. This one. I just get a capture an image, right? I think I call it window or something. Let's see. Yeah. So let's see if I can. Oh, okay. Wow. Wait a sec. This is not something I want to show yet. Let me go back. I think it's here. Let's see. Called window here. So again, I'm using surf this time, and I try to match the descriptor here. So of course here this. Okay. So here is better match now. See, like this is the one I just image I captured earlier, right? And then I trying to get the match. So it's pretty quick. So of course my laptop is reasonably fast, but no GPUs and so on. So if you guys are using what just a Nano, maybe it's probably it's fast enough for this. Right? So and let's see. Now it's quite okay still. Like you got a lot of bad matches still like coming up, but when I have the white one, it did okay. This significantly better here. So the last one, that's one probably I want you guys to. I may form a homework for that. Is like this one I didn't use a okay. That's this time like I'm not showing you the solution now. Because I won't ask you guys to use the command here. Here I use the command, find homography. So, but this time I will ask you guys to just solve that because we go for 2 lectures, just a simple linear algebra things where you can write it down very simply. But of course, may not be as fast as this one here. But for some reason, this one is not very stable. I find that sometimes it will crash. I don't know, I rarely get homocity crash, but this one seems to crash. So, is doing something pretty interesting. What I'm doing is like, I'm doing both match, I'm trying to warp. So let's see, I think I'm trying to warp the original photo to, oh okay, I'm getting quite confused what I did. I'm warping which one? I get confused. I think I'm warping warping the capture. No, I think it's not. Oh, I think it got crashed or something. No, it's not. So sometimes you see it fails crazily. So because I don't got the white matrix now. Like it found the homography is totally wrong. So it warped to some. But of course, I'm doing kind of this real time now. So and I'm actually it was quite fast. It's faster than I expected. So I think I'm let me just go back to the let's see. Here, like I already using RANSAC actually, but I guess I may be able to tune the parameter somehow to make it like more stable. Maybe some of this threshold value when I do the matching and so on. I assume if I'm not using RANSAC, it will be even worse. But again, I probably create another homework like just have you guys tried to implement the warping, like just how to find the warping matrix and then try to warp it, or maybe just try to find the warping matrix and like leave you guys to do the warping. And then also, have you guys tried to implement RANSAC as an extra bonus or extra credit? So I have my homework from last year. I don't know whether I have it working now. I didn't check earlier. Let's see. And my last year, I wrote something like with MATLAB myself. So, but I will prefer you guys to use OpenCV actually, because as you know, like once you really implement on some like real-time platform yourself, as for example, you guys were saying like do this capstone project, like MATLAB is kind of useless, right? So, yeah, if you use OpenCV, I'm quite sure you should be able to find ways to install OpenCV on those platforms there. And let's see. But I probably should kill it first. Did I kill it already? Like it looks like using lots of. Let's shut it down. Yeah, I'm going to run MATLAB because I go into wow, it's so slow. I guess I'm running out of. Okay, actually I'm fine. I don't know why it's so slow. I don't even quite remember which command is that. Okay, so this is another example. But in MATLAB, I probably make it a kind of create a kind of something with update this with like OpenCV somehow. So, but the idea is the same, right? Actually, you can write. Oh, there's so much coming up. So this is example to do stitching, like for. So for example, this one here, I got matches from 2 photos. Then I can compute the homography, right? Compute the homography and then like kind of this stitch down pretty well. Like you can see like align pretty well. Okay. And so can have another scene there. Let's see. Actually, by the way, I think this may be Wuhan, the epicenter of the virus, if I remember correctly. Yeah. So, is that I forgot? Like I forgot whether. Oh yeah. Anyway, so do you know where is this? So let's see. I got matches. I think I have this screen. I'm like I forgot what this mean now. Like because I wrote this code like a couple of years ago. I don't know what the different circle means. But if you use RANSAC, like for example, like in a more stable case, like here, as you see when I do this OpenCV demo, I count like my handshake and so on. So it's not very stable. But if you're working on photos like this, the result typically is pretty good. Yeah. So and so on and so on. Yeah, there's another one. So basically, all of them work pretty well actually. So this one is a bit too much. I guess it doesn't have like enough matches there. I'm not even sure. Like it's possible for me to get the warping completely correct somehow. I don't know. This one is just a bit off. But out of like I have like 6 cases. Like all of them work pretty well, except one. And I think I didn't use safe even here. I use I used the simplified version of SIF. So in the sense that I didn't include the rotational invariance. If you remember that if I need rotational invariance, SIF is basically doing this kind of HOG filter there, kind of like histogram of oriented gradient as feature. And to make it shift invariance, when you compute all these histogram, you pick the histogram that's largest and you just rotate the image to make the largest histogram, like Poynting loft, something like that. So I didn't do that. I didn't include that part. So, but just for this kind of application, it's sufficient actually. Yeah. So okay, that's basically it. I guess I'll start with something. So I use up like half an hour. So, but I will start something new anyway, like today. So okay, so let's talk about optical flow. So we'll start with something new today. Why is so okay? Anyway, so optical flow is very similar concept to like what we have been doing, like, but you can think of like when we do this feature extraction and do this matching here, it is working in a sparse as a sparse problem. Like you only get descriptors like from some of the points, and then try to match some of the points there. Optical flow is a little bit more, you can think in the sense that a little bit ambitious, that you are trying to get the matching for the entire image. But then, of course, if you want to get the matching for the entire image, then you need to put extra constraint on that. The extra constraint typically will be when you have image 1 and image 2, in most typical scenario will be like the image 1 and image 2 are 2 frames of a video stream. So you basically have a slowly moving video stream. For example, this one, I don't know whether I can play this. So I don't actually, but say you have a video stream that like capture this environment, this scene here as the cars are slowly moving. It's not slowly, but it moved from the first frame to the next frame. Then you just look at like how each pixel is supposed to move, something like that. So, and so to solve this, we need to do some assumption here. And as you know, like this is totally 2D. Like this is again like something not 3D. So we just like look at like the image there, and we look at each pixel how it looks like it's moving, something. Yeah. And as I said, like we need to make some assumption here. So the apparent assumption is like, okay, we will assume that like the 2 frames, like from the first frame to the second frame, is the object doesn't move too suddenly. So or like the environment the lighting doesn't change too rapidly, so that like you have a pixel in the first place here. Let's say I have a pixel here. Next time I move to here, so I'm from here move to here. The color and say the intensity doesn't change too much. So I assume this so-called brightness constancy. So I assume that like the points just look the same, like here and there. And then also like I will assume that the motion is reasonably small. So it moved from here to here, but it won't from here to move to say here, something like. So it's a reasonable assumption if I am really working on a video stream like 30 frames per second, like first frame, and then the second frame is like basically 30 milliseconds later on. And also I need the spatial coherence assumption. Basically, if this point moving here, the labeling point is more or less moving in the same direction also, most of the time at least. So if you think of like lots of rigid object there, you have the entire car there. Over the entire car, like you can expect like the points on a car, a pixel on a car, like most of the points there are moving more or less the same direction there. And the displacement is more or less the same. So this is just repeating what we just said here, the three assumption there. So now then like we with this assumption here, then we'll just say like the displacement for each of the pixel here. Let's say now you consider each of the pixel as a pixel xy here. Ixy is the intensity, and t-1 is basically the t-1 frame here. For the next frame here, let's say the displacement for that pixel here move to x plus u and y plus u now. And note that like u itself is like a function of xy, right? Because like for the entire image, like they can move like everywhere. So even though like I said like I have this immediately I forgot the name of this assumption now. A spatial coherence assumption that like labeling pixel is moving more or less in the same direction, or like have the same amount of same displacement. So with that, like I don't know why these equations like stick here. So with that, I can do a Taylor series expansion, right? So wait a sec. So basically, this one I can expand like this way. So this is approximately equal to the previous frame plus the gradient for in the x direction, and the displacement is basically u, right? So times u xy here. And similarly, gradient for the y dimension multiplied v xy here, and multiplied by it, the gradient along the the time direction there. And okay, the change is what? The change is just one, right? One frame, so it's multiplied by 1. I can ignore the 1 there, right? So that's clear. This is just a first order approximation of this guy here. Okay. So then, like with that, I can just look at the difference, right? So look at the difference of this guy with this guy here. So I assume these two are supposed to be the same, right? So therefore, like I should have like this one. Now this guy I can write like this minus this. So I get this one cancel here. So it's equal to just this guy here, right? I mean ixu plus iyv plus it here, and I want this is kind of equal to 0. So something like that. So I just want this equal to 0. And of course, like ix, iy, it, something like we know how to compute that. Like is you can just approximate that with filter, right? You have a filter, and you basically just use a filter 2D, like say in open series, like you have a kernel like this. For x derivative, you just have kernel of this, y derivative, your kernel of this, and then like in t direction will be like this, where the current frame, like t frame minus the previous frame, like this one here. And then I also have something like stick like that. So again, we have this equation here, right? So let's see. And we are trying to solve like u and v, right? So I have this equation. I'm trying to solve u and v here. And the problem, of course, like I have this uv in general is like for every pixel I'm supposed to have every different u and v. But of course, I have this spatial coherency like condition. I can assume that neighborhood to be like similar uv there. So then immediately, okay, I guess I think I can skip this. Immediately, the first simple solution will be so-called this Lucas-Kanade solution or like method. I want to solve this one, but I don't have like enough equations for that, right? But for just the u and v here, because u and v is different for every pixel there, but I can. Okay, what can I do? Like, okay, again, I think like I need to pause a little bit. Otherwise, I should give you guys some time to digest. What should we do next? The most obvious thing. So I have this problem now. Again, like maybe I find somewhere I can just draw the sooner. So again, I have basically something like I have a gradient over t. So gradient over t plus this gradient over something like that. This is x and y. Or like I can even write like basically I have something like that. Partial I partial x times u plus partial I partial y times v is plus this change in t. So partial I partial t is equal to 0. So as I said, we have something like that. So or like we need to solve u and v. So I can write in a matrix form something like partial I partial x partial I partial y plus partial I partial t is equal to 0, something like that. So for each of the pixel, I know what is these guys here. So we need to solve for uv here for each of the pixel. And this is how we derive that is based on this brightness consistency condition. Would be how to spell brightness. Constancy or something like that. Assumption there, brightness constancy assumption. And also we essentially we also use this small I forgot like that we assume like the variation of UV is cap small. I forgot what's the name of the assumption. So what should we proceed? Like we have a problem like this. If you know how to do it, you have a really good paper in 1980. So this will work like in 1980 basically. The Lucas-Kanade, and it's still like very famous. So we have 3 assumptions here. We only use 2. The third one is spatial. What's it? Oh yes. Thank you. Like it's good to have someone have good memory. Coherence. Yeah. Spatial coherence condition. So we use this to basically create this equation. So we haven't used this yet. But how can we use this? Yes.
Try to find the correlation or the least square fitting.
Yes, we are least square, but this one is not sufficient. We only have one equation here. If I write like that, I have like two unknowns here, right, each time.
Then try with the third and the second equation to come up with the other equation and solve them at the same time.
This is same thing, right? This is same thing here. So when I consider per pixel, let's say if I consider pixel x, y here, a pixel x, y, I call it p here. For that particular pixel, I have one equation, this like up for vp, and this actually I didn't write it down, but it's a more or less a ix1. This is equal to p, right, at location p. Let me write a little bit better. So something like that, right? So per pixel, like, I only have one equation here, but I have two unknowns here.
Inside a pixel.
Yes, usually small pixels, right? So actually, this first Lucas-Kanade is super simple. Right? You think of that, like, it's a really good paper, but it's super simple. Once you build this, but of course, I guess the difficulty at that time is building these two here. I will just introduce this couple like condition here, assumption here. So then the next thing I can just assume, okay, the labeling is the same. So I have like, let's say up or like ux y will be equal to ux plus 1y, let's say, right? Then that will be the same. So then I will be having like more than one equation now. So I can have like, for example, this is at p here, or like at xy here. Del y at xy here. I have let me write up vp again, is equal to minus this partial I partial t at xy here. And again, like my xy, my p is like xy, let's say. Then, but my x plus 1 is the same thing, right? So then I can stack aside the equation, right? The equation is like x plus 1 y, x plus 1 y. So then already I have two equations. Actually, I can have more. I can assume, like, for example, I have a 3x3 box, like for u here, like for the west, like this all are the same. So I will have like 6 equations here. Then again, we will go back to what we have like last time. It's just a system of linear equations. Then we can solve this. So the solution is like, if I call this a here, I call this whatever b here. So for example, I have x plus 1 y. Then my uv here, or if I call this x here, then x is again is just the pseudo inverse of that. So it's like a transpose A inverse, something like that. So that's exactly what Lucas-Kanade did. So if you use an even larger window size, you use like 5 by 5, then you have like 25 equations there. Then you just solve this linear kind of like a kind of set of linear equations. Then you solve for the d for each of the pixel. And by the way, like, it didn't end there. So we also write it down. Okay, if I have this, the solution I know is like A transpose A, right? Actually, A transpose A is equal to A transpose B. I put this thing here inverse like to the other side, but actually, yeah. Earlier I write like this, but of course this is the same for like A transpose A times X is equal to A transpose B here. So I supposed to solve this one here. And this A transpose A there is, I can write it like this, right? So if I have an A transpose for this guy, you see that, right? Do I need to go further on this? Is that obvious? Like, A transpose A is equal to this. Maybe okay. Maybe let me try to write it down there. So I have A is like so now A is something like have a bunch of equation that is like Ix at different points here. Let me call it like this is like it use a 5x5 box, right? So we have like 25 of them. So maybe I just call it Ix1 up to Ix25, and this is Iy1 up to Iy25 here. So and this is A. So then like A transpose is like flip that, right? So then it's like Ix1 up to Ix25 and Iy1 up to Iy25. So then this multiplied by that, I have something like, basically like this is what, 2 by 25. This is like 25 by 2, right? So then I have this element would be just like this row multiplied by this column, right? So it would be like Ix1 plus Ix2 and so on up to Ix25 and Ix25, right? So then I can just write it as a summation, right? So as a summation will be something like Ix, say Ixj, or and j is from 1 to 25, let's say. And similarly, I have like this Ix, j, Iyj, also like j is equal to 1 to 25, and so on and so forth. This like Iyj, j equal to 1 to 25, and so on. This guy will be just the same, so it's symmetric. So so therefore I have something like that, right? Then you look at this one here. Actually, we've seen something like this before, but probably you don't realize this. This is actually the M matrix we have for the corner detector. If you this guy. So what we have, the problem is basically this again, like this A transpose A multiplied by this guy is equal to this, right? Or like we want to solve this UV here, this take the inverse is equal to this guy. So actually when we do the corner detector, we kind of just look at the eigenvalues for this guy. We want this to be big, right? So when this guy to be big, then we say it's a corner or something like that, the eigenvalues. And here actually I have like a even more interesting kind of like, if you think of this kind of theoretically what's going on. So if A transpose A is kind of like have eigenvalues small, like both of them small, you are having a corner detector. You basically have that area is a smooth region there, right? That is not likely to be a corner. And if you think of that, like when this is small, the eigenvalues of this guy is small, then A transpose A won't be invertible, right? Or like it won't be stably invertible, right? It's like this is something like, if you think of the eigenvalues of this guy small, if it's similar saying that this guy is something close to 0 in terms of the determinant. So if you take the inverse of this guy, the inverse of this guy tends to be like goes to infinity or something like that. And this is exactly what's going on, right? When this is flat, like you will have not a stable solution here. You try to solve this UV, you won't have a stable solution. And actually, this also happen if you have taken a course like in numerical analysis or something like that. We have something known as the condition number. It's like of a matrix. It's like the largest eigenvalue over the smallest eigenvalue. And in that case, it's when this one is big, again, like the solution won't be numerically stable. And this is the case when, remember what's that? What's that case when one eigenvalue is much larger than the other one? Yes, but when will that happen physically? If you look at seeing that like one eigenvalue of this guy at that, for each pixel I can compute this one, right? For each pixel I compute this one here, and then I look at this matrix and say like one eigenvalue of this matrix is much larger than the other eigenvalue.
Is it like a corner?
No. The corner is what? Corner is like what?
One eigenvalue is way higher than another one.
Yes, one is way higher.
At least for the first part.
There's several different cases. So I remember. Okay, either a region can be kind of smooth. Yes, that's okay. But so and if like it's an edge, this solution you try to obtain this UV won't be very stable as well. So why so? It's reasonable as well if you think of, say, if I'm at an edges, I have this kind of problem, right? I just look at a region here. Let's say I have an edges. I want to see like how this line move. And this problem is not defined, right? Because if I look at this just tiny region here, if my line move from here to here, my motion can be either this way or this way, right? It's not a unique solution here. Like both of them give me the correct solution, right? So only when that's corner, only when both your eigenvalues are big, then that region is either pretty noisy or like a corner. Then like you can say for sure that like okay, when you solve the UV is kind of a stable like numerically correct solution, something like that. So anyway, like but this is the Lucas-Kanade. So we just compute this M matrix just like in the corner detector, like for every pixel, and then like also of course you compute this A transpose B here for every pixel, and then you just take the inverse for that guy. But as I said, like you can get like lots of solutions there, but not all of them will be very accurate. For example, like if you remember this kind of same image here, like we show like for the corner detector, for here we can get a pretty accurate solution there, the motion, but at the edge here and also like for the smooth region here, like the solution won't be very accurate. So, but that's the Lucas-Kanade and one refinement is that like we can do this step like multiple times. So this is like the idea actually used like not just for Lucas-Kanade, but you can use like all of this like optical flow method. So let's say if I try to find the first, okay, I try the solution of the warping, like for, the displacement for the entire image now. Then I can repeat this that way. So basically now I know each of the pixels like supposed to move from here to there. Then now I can just take the first image and I actually warp that image to that new location. And then of course I have a new image. Then I will just try to repeat this algorithm for this new image with the reference image again, and then I can repeat this multiple times. So this is a kind of like trick that can be used like for all this kind of algorithm here. So this is one of the methods. So we'll kind of let's look at like a couple more methods. Maybe I just look at like one more, like this Horn-Schunck. I don't know how to pronounce that, but then maybe yeah. So this is kind of a generalization of the Lucas-Kanade. So Lucas-Kanade, the idea is pretty simple. Right? I just like force like for a particular region there, basically the displacement will be the same like in that region. So and here I will just instead like for the spatial coherence constraint, I will use a kind of regularization to kind of put into the problem there. So remember that we are trying to kind of like make this guy zero, right? So I can introduce a kind of like an energy function. So basically this part here, originally I want to make it zero, but at the same time I want to make have the spatial coherence. So then in the sense that if I have the UV, I can think of the UV is like also a 2D function, right? And then I just want to make the UV kind of smooth. So then I can introduce this gradient of U and gradient of V. I want to, this is basically compute, so just the regularization. I want to make the change of UV in both like XY direction to be small. And I can put an alpha here, just, I don't know, parameters to kind of trade off the energy function somehow. So it just makes this constraint stronger or weaker. Then afterward, then I just want the entire, this is just for one pixel, right? Then I want to have all the pixels like to be small. So then I can just like integrate the whole thing. Then I have some kind of energy function like that. I just try to minimize that. So does this make sense? So so I have something like this, and I'm trying to solve U and V, and I don't know, like you guys taken some course in physics or something like that. Like in physics, you may look at you have similar problems. Like this is a some kind of least action or that kind of problem, like Euler-Lagrange equation and so on. Yeah, or there's another name in math like calculus of variation or stuff like that. So, but okay, you don't need to worry about that. We can go for first order. So just think of like first order. I mean like first principle, like how to tackle this kind of problem. Again, I can just like think of like, okay, I will just try to do say what I'm trying to do. I forgot. I can do a Taylor series expansion, right? So I have this one here. So let's say I call this whole thing here just L here as a function of U and V. Actually, it's not just a function U and V, but also like the also function of like, you see I have a gradient of here, so therefore it's also a function of like actually more precise, I should say that it's also a function of partial U, partial X, or then maybe I can write it as UX and partial U, partial Y. Right? It's also a function of ux, uy because here is this one is a partial u partial x squared plus partial RANSAC. Yeah, partial u partial y squared, right? So this whole thing L here is actually a function of like uv and ux and uy here, ux and uy here. Now I can say I want to minimize this. It looks pretty complicated, like E here, because E here is like integral of L here. L itself is a function of uv and also ux, uy. So E also is a function of ux, uy, and u and v here. Wait a sec. Ux, uy actually have like vx, vy also. Actually, I'm missing here. For this guy, I also have like vx, vy. I cannot. Okay, that's okay. That's fine. So, and then like to minimize that, so you can think of like similar to a just any function like I, and if I want to minimize that function, I can just make the gradient equal to 0. So, and now, but of course, my variable here is basically uv, and actually consequently also like ux, vx, uy, vy, something like. And I can just try to see like if I make some changes on u and v. Let's say if I shift u and v by a tiny value, let's say by u tilde epsilon and v by v tilde epsilon. And if I shift that by a little bit, so if this is the maximum, so think of like if I have an I function here, maybe something like that. I have this I here. If this is a maximum somehow here, so if I shift a little bit, like I should be like at the peak here, right? Then the take the derivative should be just equal to 0, right? So then I can approximate this derivative like that. So it's like I have L here. I change a tiny little bit, and minus my original L there, and over this epsilon here should be just equal to 0. Right? So then for this guy here, then I can again just first order use a Taylor series expansion. So L now will depend on like uv and also like ux, uy, vy, vx, vy, right? So I will basically move vary u, okay, yeah. Move by like epsilon u tilde, v move by like epsilon v tilde here, and ux move by epsilon ux tilde here, something like, and uy move by like epsilon uy tilde here, and so on. So therefore, the first order expansion is like this, right? The whole thing is like this here. And of course, I minus this guy, I can just cancel this, and then I want this one over epsilon, it goes to 0, right? So I can basically the epsilon get cancelled here, so I have this goes to 0. Something like I want this guy, right, goes to 0, right? So this one goes to 0, this integral goes to 0, also means that something inside it's not always, but this one, if this one goes to 0, then I can ensure that whole integral is going to 0. So that then I can try to see how can I make inside is going to 0, But first of all, okay, this one go to 0. I can do some integration by parts here. Let's see. I have, let's see, where the, okay. Yeah, I want to have U tutor and V tutor. I have UX tutor and UI tutor and so on. So I can first absorb that, so I can write like UX tutor as a DUX tutor. Right? DUX tutor will give me UX tutor DX, something like that, right? So therefore, like if I just look at this one here, this term here, so UX tutor DX is equal to DUX tutor UX, right? If you remember integration by part, this is equal to, if I have some integral here, is equal to UX tutor UX minus UX tutor DUX, right? DUX will be I'm sorry, like I made a mistake here. Here it's equal to DU tutor. DU tutor. Yeah. Or like I should write partial U tutor, partial X, something like that. And so this is U tutor here. This will be U tutor here, and this will be like U tutor D UX. So it will be like U double X DX, something like that. So therefore, like you see this term here, and this guy, like if you take okay, this guy basically 0. If you consider the boundary condition, so this guy will be gone. So you just have this one. It will be just equal to this guy here, UXX and U tutor, something like that. So for the rest, it will be similar like this. So okay, I don't know. I guess maybe I will repeat this like next time. I guess it's better I just maybe okay, maybe I will just stop here. I feel like you guys we don't have yeah, we will be over time anyway. So I guess I will come back next time. Say. Probably this weekend. Yeah. Yeah.